Last questions about the final exam. Monday at 8 a.m. Right here.
How long is it going to, like, how long is the test?
I think it's 7 pages.
Great.
It
should take the whole time.
Where the test you just took was 5.
Okay.
So it's a touch longer than a typical test. Not quite double. You have double the time.
It's structured the same way as all your other tests, right?
Yes. There will be a good amount of multiple choice. There will also be, for the multiple choice, there will be a Scantron to use. Recording your multiple choice portion on Scantron. There will also be written portion like mechanisms and short answer type stuff. Just do the multiple choice on the Scantron. Yes?
Will you be providing a Scantron or do we need to bring our own? Will you be providing a Scantron?
Yes, I will provide. You need to provide a pencil, I reckon. Other questions?
And there will be mechanism questions as well, right?
I could tell you what's on there. It's just like it was on test 1, 2, and 3.
Okay.
Everything you expected there. Just like test 3. Questions very similar. There'll be questions that were not on test 3 that did not make it into test 3, but you were hopefully prepared for them.
Will you miss us?
Do what?
Will you miss us?
Will I miss you?
Yes, I'm so devastated.
This is the first time that I can ever remember that I've never followed up with Organic 2. Not particularly happy with that, but that's the way it is. What's the, how much does the exam count? 30%? Exams count how much? 45? 45, lowest drop. Okay. I will say this: if you'd like, I can switch the test and the exam ratio percentages. Make the exam count 45%.
Yes. No way. No, thank you. Can you let someone one up?
And only if it helps you. That is.
If it helps. Our yes.
That is, if you bomb the exam, then it'll count as on the syllabus. But if it helps you, I'll count it 45% and count the test 30%. Would that help? Because that would give you more of a chance to raise a grade when they're good at the exam. Okay, we'll leave that.
Who got 99 this time?
Only if it will help you. If it doesn't help you, we'll count it as on the syllabus. Okay, radical reactions. We looked at one radical reaction before. Mainly it was the an alkyne. We can do a radical reaction to get a trans-alkene. That was dissolving metal reduction with sodium. That was a radical reaction. You have the trans-alkene. Cis-alkene comes from, how do you make a cis-alkene from an alkyne?
Precious
One.
metal powders. Precious metal powders.
What type then? Because poison. If you don't use a poison, it's going to go all the way to the alkane. It'll be a double hydrogenation. You need to stop at the cis-alkene, right? Okay. We have other radical reactions. And here we go. Largely halogenation. The first reaction is an example. And of alkanes. Here's a typical alkane. What type of reactivity does it have? Is it a good nucleophile? Doesn't have a lone pair. Doesn't have a pi bond. Alkene chemistry, pi bond acts as a nucleophile. Substitution elimination, you got a lone pair that's acting as a nucleophile over base, and something with a leaving group. Does this have a leaving group? So it can't be the electrophile, the thing, okay? What type of reactivity does it have? Not much. You can burn it and produce heat. Okay, we showed this on one of the original alkane handouts, that it, not much reactivity. None of the reactions we looked at, can you do anything here? Okay. But you can do radical halogenation here. And this is an example. We'll take an alkane with like elemental bromine. Theoretically, you could do any halogen, but usually only bromine works out well here. Mainly because of the thermodynamics. We'll mention a little bit more. You take elemental bromine, add a little light or heat or peroxide, and we can get a reaction, and we can get this product here. Now, this is a substitution reaction because you see the H here, right? Now, day one, you didn't see the H there. You see the H there, right? Okay, there's an H there. It's now gone. It's replaced with the bromine. It's been substituted. Substitution reaction. What's the byproduct of this reaction? The small molecule, non-organic byproduct.
Bromide. Bromide? The bromide ion?
Well, I mean, but completely.
HBr.
HBr, yes. Okay, the fate of the H is with the HBr, and then this was Br2. One bromine's incorporated, the other becomes, so we also form HBr in a completely balanced line reaction. This reaction is typically very regioselective. Hopefully that means something to us. What does that mean? The bromine is only going to bond in this region. At that region, the bromine ends up there. Where does it end up? Do we just want to say there, or can we describe there? On the
Tertiary carbon.
On the tertiary carbon. Yes, we have some terminology, right? It's going to be regioselective for doing a substitution at the tertiary carbon. We'll look at this mechanism here. Before we move on, though, let's compare it to an alkene reaction. Now we have these pi electrons that can act as nucleophile and attack. And now we have a mechanism that we can think about. And we know that this reaction leads to what type of product? A dibromide. Alkene, dibromide. And if we had stereochemistry here, we know the bromines would be trans or anti. Backside attack bromonium ion. Yeah? So, you get two bromine, and what's the byproduct here? There is no byproduct. It's a plain out addition. You're just adding something to the starting. So contrasting the alkane versus the alkene, which this isn't what we know. You did this reaction in lab. Then you double E2 eliminated your product. Okay, let's look at the mechanism for the radical bromination. The first. Maybe I'll bring it back down and start with what's written here. We got bromine, right? We've got this. We know we're doing something with this H. Let's draw it in. Comments about the test. I mentioned it before, but you guys have got to be more particular with your mechanism arrows. I mean, if you got an alcohol here and you got HCl, just doing this is not sufficient to show protonation. Okay? Because if this is covalent, that means you've got to break this bond and you would need something like this. Or you can just show it ionic. And I've always done this. Now it's okay to just do that. But just something towards just this is not really enough clarity. It lacks precision, it lacks detail. The other thing is, Something like Cl minus is not a base. Many of you deprotonated an alcohol using Cl minus to make maybe something like O minus plus HCl. That's not a base. In fact, we said in class that hydroxide, which is a base, will not even deprotonate a regular alcohol. So if it won't, how would this? There's a huge difference between this taking this H and this is important going into organic 2. You'll see this all the time. Taking care of proton. That's the subtitle of organic 2. Taking care of protons. And biochemistry. Dealing with protons. Acid base. This will take this H and leave these electrons behind. What's the difference between these two H's? This one's way more acidic because it's on a positive oxygen. And when you give the electron, you go neutral. It's okay to take an H here. Anything can take this H. This here, you're making an oxygen anion. It takes a strong base, and hydroxide won't even do it. Typically, we have to do it with sodium. There's a difference between taking a neutral, H from a neutral, and taking an H from a positive. Okay? Yes, this is acting as a base when it takes this. But it's a lousy base. How do we know it's a lousy base? Because it's the conjugate base of a strong acid. Conjugate base of a strong acid is by definition very weak. Very strong, very weak. Please keep that in mind. The other thing, in the Williamson ether synthesis, a lot of you guys, with the phenol, you use sodium. By the way, when you do a synthesis, typically you want to have some, like first and then second, some steps. First step, a lot of you said sodium. The second step was a big molecule with a leaving group. Okay, it's kind of big. Use sodium. That's overkill. Better to use sodium hydroxide. Sodium is only needed with a regular alcohol. It will deprotonate a phenol, but it's overkill. This is like killing a mosquito with like a bazooka. You don't need it. With phenols, sodium hydroxide, much more common, safer, etc. This, of course, will work. I'm just telling you, it's just overkill.
Does it make a difference if it's sodium metal?
It's got to be sodium metal. What other sodium would you use?
I mean, I don't know, because you have the little circle on top of the sodium, so I thought that would make a difference.
You see, if I don't clarify, it's like, what are you talking about? That's why a lot of times people do draw those. The other way would be I'd have to draw an ion. I didn't do that. Yeah. That's sodium metal. A lot of times people do draw a zero to say oxidation to 0. No, sodium ion is not a base. It's just a spectator ion. Sodium ion is not going to do anything. Anything. Anything to anybody. Just a couple of miscellaneous things. But dealing with the proton, very important in organic 2, and also just more clarity on mechanisms. So a lot of times when I just circle things, that means it's just lacking. Okay, so that H was there. We got to get rid of it somehow and replace it with a bromine. Let's see. All right, first step is something here. Something here is going to form bromine radicals. It can be done with heat, it can be done with light, or peroxide. Any of those will make this happen. This is a fairly weak bond. These guys are very headstrong. They don't like bonding to each other. We can put them in this position, maybe with electricity to make bromine, but they don't like it. High reactive. With a little energy, okay, is this thing going to ionize? That is, will one atom take the electrons and become minus, leave the other one plus? No, bromine ain't going to want to become plus. It's not going to ionize like HBr would. Here, Br minus H plus. It doesn't ionize that way. Instead, main chemistry here, especially with a little energy or chemistry, is to do this. One electron goes this way and one electron goes the other way. Now we started with 3 lone pairs on each. That is, this bond here does this arrow mean? This is a fishhook arrow. Okay? This is a regular mechanism arrow. This is a fishhook, or a single-headed arrow. This is when you're moving 2 electrons. This is when you're moving just 1 electron. And 99% of the time, we always have moved 2 electrons, like a lone pair, that's 2. Or a bonding pair, that's 2. Here we're moving 1. 1 electron, there's 2 electrons here. 1 electron goes to this bromine, and 1 electron goes to this bromine. So you end up with, over here, 1 electron on the bromine. What's the other going to look like? Same thing. 1 electron on bromine. So I'm just going to draw 2 here. Is that okay? You get 2 of those. What do you call this process? The bond has been cleaved, but you end up with sort of the same result. That is, electron on each. So each got an electron. It's called homolytic bond cleavage. Each bromine ends up the same in terms of each got 1 electron. Up here, it would go like that, right? And you would get H plus, and the bromine would get them both. Okay? Both electrons go to bromine. And so you don't get the same. It gets 2 and it gets none. This is called what? Heterolytic bond cleavage. Whenever you do ionization like this, heterolytic. This is called homolytic bond cleavage. It produces what? 2 bromine radicals. Something with an unpaired electron is called a radical. Is this bromine charged? That's just double. Is that bromine charged? How many electrons does it own? 7. How many is it supposed to own? 7. It's neutral. Neutral. Bromine neutral. But does it have an octet? No, it only has 7. No octet. But it is neutral. So it's a little bit atypical, yeah? Okay. This creates bromine radicals. Now I'm not going to show exactly how these do it. The light, a lot of times light, you see people draw like a light bulb. I can't draw. Anybody know how to draw a light bulb? And you see something like boom, like light being put into this bond, okay? That's not a mechanism error, just light shining. Sometimes books will kind of show that type of diagram. And the light energy will cause the bond to homolytically break. Okay? A lot of physics. I'm not going any deeper. Heat will also cause this. You can also do this with peroxides. When you do it with peroxides, it's probably 1 radical, because these create radicals, and these radicals make these form radicals. I'm not going to go into mechanistically how they're. But anytime you see any of those 3, you're making bromine radicals here. Now the peroxide could be as simple as hydrogen peroxide in your medicine cabinet, or it could be some more fancy organic peroxides. What is peroxide in general? I think we said before. Peroxide in general is where 2 oxygens are bonded together. If these are H's, that's hydrogen peroxide, right? Medicine cabinet. Oxygen bonded versus like bromine bonded. You see, this will also want to homolytically cleave. And sometimes it may do it even easier than the bromine, or maybe not, but it just gives you more radicals. It's also maybe, I don't know, just throwing stuff out. Maybe the light here makes that form radicals easier than this, and then those radicals make this. Mechanistically, let's move on. Bromine radicals can be formed. Okay, from here, now we can get going. I'm going to start here and then we'll move down here to some space. Got bromine radicals. This is how we typically show this mechanism. This electron will team up with 1 in the bond here. So one of these electrons will go here and team up with that one. The other electron in this bond will move just onto the carbon.
These are all fish hooks, right?
Do what?
These are all fish hooks. All 3 arrows you just drew were fish hooks, right?
All concerted, all together now?
They're all fish hooks.
Oh, yes, they're all fish hooks. We're moving one electron. This electron goes teamed up with one of them in the bond. The one that's with the H, the other electron moves onto the carbon. What does that give? We can, okay, we have boom, boom, boom. What is now on this carbon from that arrow movement? One electron. See, that's what that arrow means. One electron moved onto the carbon. The other electron and the H nucleus teamed up with the bromine to make what? Here's the original bromine. It had one electron. But see, we brought the H electron there too, and it teamed up. This is now a covalent bond, and what is this? Well, that's HBr. That's your byproduct there. Basically, bromine radical reacts to give this. Why did we make the radical at the tertiary carbon there? Why didn't it strip an H out of a primary or a secondary? Well, it's the same as a cation. Radicals are electron poor. By the way, what's the charge of the carbon?
Neutral.
It's neutral. 4 electrons. But it has no octet. 2, 4, 6, 7. No octet. Even though it's not charged, it's still electron poor. And so we can treat it just like a cation in terms of what stabilizes it. Radicals are better at tertiary carbons because, just like a cation, it's got 3 rich friends that can donate electrons towards it. So you look at it the same way as a cation. You'd rather form something electron poor at this carbon as opposed to one of these, right? That's why you get your regioselectivity. Okay, how do we get the final product from here? We've already made our HBr. What do we need to do to get final product? We've got another Br radical. We could team this electron up with this electron. Boom, boom. Electron, electron makes covalent bond. What would that give? Product? Hey, I've got an electron, you've got an electron, let's share and make the bond. Boom, we just shared and now we're making the bond, right? One electron, one electron. That's it, right? There we go. That's an arrow with only one line. It's a fish hook arrow. Both of them are. We're only getting one electron. Well, it's kind of like this. It's kind of like wonder twins. Here we go. You have an electron, I have an electron. If I just take this electron and move it over there, it's almost like I'm taking it from me. Well, maybe not. It's more like let's meet in the middle. You move your electron in the middle, I move mine in the middle, and we come in the middle. So we're moving both electrons. That's just the way typically it's shown. Because on the other hand, if we had a carbocation, and you had something like water, how do you make a bond between here and here? These electrons go bond. But this is a regular error because there's 2 electrons here. And you're going to make a 2 electron bond, but you're moving these two to initiate. It's like you don't have any, but I've got 2. So why do I want to move it? This atom doesn't even have electrons, so why would you even use an arrow over there? You need to move these 2, and again, when we talk about moving arrows, this is not chemistry. This is our method of showing reactions on the board or on your paper. But this is organic chemistry, being able to show mechanisms. This is not a chemical phenomenon. It's us. It's our practice of how we show this. Okay, are we done? Did we make the 2 products and show mechanistically with arrow movement? It looks like we're done. Problem is we're not, because this is not the mechanism. If it was, let me ask you this, or see if you can answer. It's known that if you're using light, you only need to shine the light at the beginning. once the reaction gets going, you can turn the light off and it will keep going. How is that? If the mechanism was how we just showed, well, we can make one molecule this way. One molecule. How would you then turn around and make the next molecule? You would have to come over here, and where would you start from? The next molecule of bromine would have to cleave. And you can make the second molecule. Then how would you make the third? The next molecule of bromine would have to cleave. Well, how is this cleaving? Again, if we just focus it on light. Light is making it cleave. Light. But if you turn the light off, it will keep reacting, and it'll go 3, 4, 5, on to a gazillion. How does it keep going if you turn the light off? Because light is required for this to happen. So how do you explain that? Does your mechanism explain how you can turn the light off? Let's give another mechanism that would maybe explain how you can turn the light off. Instead of this happening, okay, I'm going to redraw this radical over here and make it kind of fresh. Let's do it this way. Boom, boom, boom. We get our tertiary radical. Instead of it reacting with bromine radical, what if it reacts with bromine? That is the second molecule. It's the first bromine we cleave, and it led us to this point. Let's bring in the second bromine. And let's let it react here. One of these electrons and one of these electrons, carbon teaming up with this bromine, the other electron here goes over to the other bromine. What does this create? Well, if carbon teams up with bromine, what does that give? It gives us our product. But it also produces what? What are we producing over here? Br radical. Br radical is produced in this mechanistic approach. Since we're producing Br radicals, do we need the light anymore to generate Br radicals? You do not. You can turn the light off now. Now you can turn the light off because now the new bromine gets consumed and reacted this way. And we generate product plus Br radicals. This doesn't involve light. Light's no longer needed. Now what can this bromine radical do? Now it comes over here and reacts with another molecule of that. And you go here and you generate Br radicals, and you come over here and react with the next molecule of that. And light is not needed anymore because you now have a mechanism that creates bromine radicals. This is called propagation. Because now I can just cycle through. Every mechanistic step creates bromine radicals that can then come back and react again over a gazillion times, and then you have consumed all and done your reaction. Light is only needed at the beginning. Does that make sense? Our original mechanism would need light to generate more radicals. Okay, this is called propagation. This is called initiation. All right? Initiation is forming the bromine radicals by light or heat or peroxides. Then it can propagate on its own, and you don't need that anymore. Final step would be called, well, a third step that's sometimes used is termination. Termination would end your loop, your cycle. Termination could be a variety of steps. Maybe Br radical reacts with your glassware. If that happened, would it ruin your cycle here? If something took this other than to remove it from the cycle? Can bromine radicals react with glass? Never thought about that, right? Your chemicals reacting with your glassware? That's why when you do like fluorine chemistry, you don't use glass. Fluorine will react with glass. It'll dissolve it and stuff. What happened to my round bottom? It's now gone. I now have a mess on my bench. Let me ask you this. Is it possible to get this product? What if I told you this product may be formed in this reaction? Is that possible? How could that have formed?
What is that? I have no idea. Maybe I'm
What if this carbon radical reacted with another carbon radical of the same thing? What would that form? Two of these bonding together. If that happened, that's possible. Radical reactions are often a little bit messy because radicals can start bonding together. It turns out, though, that bromination is a particularly good reaction. It has the right thermodynamics. If you do calculations, it's good. And thermodynamically, it's driven to this product we're showing. If you try to do chlorination, it's too exothermic, and you get lots of messy products. For example, if you try to do chlorination, instead of reacting here, you might break radicals here, because it's just not as selective. You know how we talk about you've got water running down the road, and it comes to a fork. The road goes here or here. Where's the water going to go? It's going to go downhill. That's selective. But only if it's a moderate amount of water. What if a hurricane is coming through? Which way is it going to go? Probably going to go both, because you just got so much energy coming through it, you lose the selectivity. You can't say, well, it's a hurricane, it's still going to go this way. Why is it going that way? Well, because you've got so much water and wind and energy, it just goes that way as well. If your thermodynamics is not good, you can go this way as well. That's what happens with chlorine and fluorine. Fluorination is so exothermic, it tends to be a little bit dangerous. Iodine, on the other hand, is not good. Mother Nature made radical bromination just good in terms of the numbers. That's why I usually see bromine done with radicals. Okay, let's predict products here. Can you give a product of this reaction? These two here? We expect some selectivity there for the tertiary site. What's the byproduct we form here? HBr. Yeah, if you do this reaction, you may or may not be heating it, but typically this reaction will start giving off a gas. Okay? You need to have it in a good ventilation. HBr gas is given off. As this reaction proceeds, you take pH paper and hold it over the reaction, it'll turn red. That's because it's giving off HBr. How about down below? Again, when you see this, what do you see? Bromine radicals? What do you see here? What is this? This is all condensed. This is O2. It's OO. The other end's the same. I'll just draw it over here. It's the same thing. Over here, it's this CO phenyl. CO phenyl. CO phenyl over there also. It's just a peroxide. I'll go ahead and draw it over here so there's no confusion. These are called benzoyl groups. You'll see this in organic 2. So what's the name of this peroxide? If these were hydrogens, it'd be hydrogen peroxide. These are benzoyl groups, so it's benzoyl peroxide. And where do you see that at?
Organic 2.
What?
Organic 2.
You also see it in your medicine cabinet or in Walmart in the like acne medication aisle. Benzoyl peroxide, right? Common acne medication, 10% benzoyl peroxide, maximum strength. Right? Because these things form radicals like on the skin when they're applied. The radicals react with and kill the bacteria. Radical chemistry there. Okay? That's benzoyl peroxide, using it in, okay? What do we call this? Is that a catalyst? We didn't reform it in the other. Here it would be called a what? I wrote it here, I drew a line, camera. Initiator, yeah, it'd be called the initiator here. Because it probably is consumed. Since it's consumed, you don't want to call it catalyst, right? But that's a minor point. Terminology. Product here. Just bromine radicals. Where's the best place to make a radical here? Same as a cation. Where's the best place to make cation? Benzylic, right? Yeah. Product here would be benzylic bromination. Just like cation, it's a great place to make a radical. We don't have time to look at resonance of radicals. Can you do resonance of radicals? Yes, you can. How about this one here? NBS. NBS is this guy, N-bromosuccinimide. We're just replacing the other bromine with this nitrogen. It's a source of bromine radicals. Okay? This will homolytically cleave just like bromine. Maybe you see NBS bromine radicals. Okay? It's a much safer source of bromine radicals because bromine is a liquid. Very toxic, very volatile. If it's open, it's got vapors and you're going to, okay? You spill it, it's going to be all over the place, a big, huge mess. NBS is a solid, not volatile. You can weigh it out and let it sit there for, if you spill it, you just sweep it up. Much safer. NBS. Whenever you see it, it's just bromine radicals. And so we're doing radical halogenation. Where's the best place to make cation? Right here, resonance stabilized. Same thing with radicals. Again, I'm not going to show any resonance of radicals, but right? Cation there would be best because you can do resonance. By the way, guys, this is a resonance arrow and this is a reaction progression arrow. Right? So if this was, you need to use correct arrows on your mechanism. So the product here is going to be boom, boom. Right? We're going to brominate there by our mechanism that we've already done. Be regioselective. What do you call this position? That's called benzylic. Anybody remember next to the alkene?
Allylic.
Very good. Allylic. Allylic bromination, benzylic bromination. These are good sites for radicals and cations. Two possible products due to resonance. Okay. I'm not going to show that. You can take a look at it on your own. Typically, I thought the test was going to be on Friday. We would have 2 days for this. Why can't you use BR2 in the last example? Why not use BR2 here? BR2 is fine up there, but not here. If we had tried to do BR2 with H nu, It would have reacted with the alkene. Can bromine react with alkenes?
Yeah.
Yes. And that's faster. That's like instantaneous. NBS won't react with alkenes, so that's another good point about it. It'll just only do your radical chemistry. See, bromine doesn't react with benzene, not as easily. You'll learn more about inorganic too. And up there is no alkene. None of the alkene reactions we've looked at will work with the benzene. Those are not really alkenes. But that's a nice regular old alkene, right? Yeah, it'll just do your addition reaction. What's next? Why is the ability to put bromine on an alkene so important? I mean, we made this product at the very top. Why? Now you got so much reactivity. Now you can do substitution or elimination. From here you can do all types of stuff. The world is your oyster. You can do Grignard reactions, which you'll learn in organic too. You now have a good site of reactivities, leaving group, all types of chemistry now. Where you're starting an alkane you couldn't do much with, but now you can. I think we're out of time, guys. 4 o'clock on Friday. We didn't do the next pages. I'll maybe make some comments in the email I send you. I'll send you a... the first page will be potentially on the final exam.
Okay. So there's not going to be any new coverage on Friday?
No new coverage on Friday, that's just review. But this first page potentially on final exam. I'll summarize in an email to you. Friday at 4 if you want to have review.